Hello, my name is Johan Johnson, and I'm going to go over exam 3 for process control. In question number 1, we can see the figure 1, which shows the cascade control loop with 2 PI controllers and 2 disturbances. Controller C1 in the outer loop is the primary controller that regulates the primary controlled variable by setting the set point of the inner loop, and controller C2 in the inner loop is the secondary controller that rejects the disturbance D2. First, we have to design the inner loop controller as PI controller, and then design the outer loop controller as PI controller, and we have to tune the PI controllers for a target bandwidth of 0.2 radians per second and find the values for the control parameters for both of them, and then we have to plot the disturbance rejection response. As you can see, plant 2's transfer function is right here, plant 1's transfer function is right here. This is basically what I've mentioned before with the MATLAB code attached to it. And we have to tune the inner loop controller C2 with the open loop bandwidth at 0.2 radians per second. Here's the code for that. And same thing applies to the outer loop controller C1 with the same bandwidth. And we can figure out that based on the code that was provided before, KP for the inner loop controller as PI controller is going to be 1.08 times 10 to the negative 5, and TI is going to be 0.0005, and for the outer loop controller as PI controller, the values are KP is going to be 0.377 and TI is going to be 286. Here is the code for the plot of the step disturbance rejection responses of D2 for both control systems. And here is the plot of the disturbance rejection response for the given cascade control. And amplitude is going to be on the y-axis and time is going to be on the x-axis. As you can see, both cascade and single loop cojoined around 100 seconds. And as you can also see that a cascade functions way better than the single loop. Here's the reference tracking graph. Okay, so question 2. In figure 2, you can see the combined feedback and feed-forward controller system. A feed-forward controller along with the feedback controller is used to improve the output performance and the rejection of the disturbance D with the following transfer functions also given: GV, GD, GP, GM, and KM. And also we're assuming that the disturbance transfer gain is going to be 1. What is the closed loop transfer function of y of s over ysp of s if d equals to 0 and ysp is a variable? So in this question, y over y of s is going to be equal to 1 if that's the goal, and in order to come close to the goal, we have to do forward over 1 plus loop. And as you can see from the figure to the right, we're only focused on this part because d is going to be equal to 0, so we're not focused on that. So as you can see, the forward is going to be km, gc, gv, and gp, and the loop is going to be this, so gc, gv, gp, and gm. And then we have everything else. We have everything else listed on the previous slide except GC. So we have to find GC, and in order to find GC, we have to use the Ziegler-Nicholas tuning parameters. So for the Ziegler-Nicholas tuning parameters, we have to find KCU and PU, and we got to use the continuous cycling method. 1 plus G open loop equals to 0, 1 plus GV, GM, GP, and GC, and then we're assuming that GC is going to be equal to KC, and then we're going to equal to 0, and then we get this expression, and then we said S equals to IW, where we have two equations, the real equation and the imaginary equation, and both of them are going to be set equal to 0. And here on the right, you can see the tuning parameters table for PID controller. For KC is going to be KCU over 1.7, T1, tau 1, PU over 2, and TD, PU over 8. And as seen before. We basically plug in all the values, and we figure out that PU is going to be 104 minutes, tau 1 is going to be 52 minutes, and tau D is going to be 13 minutes. And by solving the imaginary equation, we can find out that Kc is going to be 0.0017, and then K is going to be 0.001, and that's the tuning parameter for the PID. And once you find Kc, we can basically plug it into the closed loop transfer function, since Kc is assumed to be GC. And once you do that, we can find out the answer for 2A, which is right here. Okay. And the PID transfer function for the GC based on the Ziegler-Nicholas method. So here's the equation for that. We've found all the values for the symbols already. Kc is this, tau 1, and tau D is right here. And then we basically plug it into here to find the PID transfer function for GC. Question 2b. What is the closed loop transfer function of y of s over d of s if d is an input? So now we're focused on this part of the block diagram. D is an input variable, and y of sp equals to 0. So the goal is for y of s and d of s equals to 0. For the actual is going to be forward over 1 plus loop, and basically by following you can find out that it's going to be gd over 1 plus gff, gd, gp, and gv. And we know that gff by looking at the block diagram, it's going to be negative gd over gm, gp, and gv. And we can find out what GFF is. It's right here. Once we know that, we can basically plug it into this transfer function to find out the finalized transfer function for 2b, where d is the input variable. And for 2c, we're estimating the static feed-forward controller GFF. So for that, we basically set it to 0. Once we set it to 0, we can find out what the S is. And S is going to be negative 0.025. And then we, once we found out what S is, we basically plug it into the GFF expression to find out what GFF is, which is the static feed-forward controller, and we're just estimating it. And here is question 3, and question 3 is asking us, why would an engineer choose a combined feedback and feed-forward controller as opposed to the feedback only or feed-forward only controller, and we'll state at least 2 advantages or reasons. According to the chapter 15 PowerPoint, we can find out that the combined feedback and feed-forward controller allows the user to have the benefits of both systems in one setup. For example, the feedback aids in the full offset of the monitor variable, while the feed-forward cannot fully remove the offset, and specifically eliminating the effects of the measurable disturbance and correcting any unmeasurable disturbances and modeling any errors. And one prime example can be seen on figure 2, which was stated earlier. So here are some of the references that I've used, and thank you. Hope you guys have a great day. Bye.